Welcome to today's YouTube tutorial on first order circuit. If you are new to electronics or looking to deepen your understanding of circuit analysis, you are in the right place. In this video, we will dive into the fundamentals of first order circuits, exploring the concepts of RC and RL circuits, time constants, and the transient response of these systems. Whether you are a beginner or just a refresher, we will break down these topics in a clear and easy to follow manner. So grab your notepad. Let's start unraveling the secrets of first order circuit. In our last video, we talked about energy storage elements, which are the inductors and the capacitors. And we got how we can calculate the energy stored in an inductor or a capacitor. Things to note for inductors and capacitors are: number one, for an inductor, it acts as a short circuit to DC. But for a capacitor, it acts as an open circuit to DC. Which means that whenever we have a DC, whether voltage source or a current source, an inductor will act as a short circuit. That is, voltage of that inductor is equals to 0. But for a capacitor, it acts as an open circuit, which means that the current going through the capacitor is 0, but there's still voltage on the capacitor. So that's the first one. The second one is that the inductor resists abrupt changes in current, while the capacitor resists abrupt changes in voltage. That is, at a particular time, t is equals to 0 seconds or t is equals to any time, the inductor resists changes. That is when it is coming from the left and when it's coming from the right, it tends to the same number, it doesn't change. But for capacitors, it resists changes in the voltage drop on the capacitor. So which means that if I want to get the voltage on the capacitor, if I have a switch, right, I want to get the voltage on the capacitor before the switch is closed. So before I can now know the voltage at that time, let's say at time t is equals to 4 seconds, we will close the switch. So which means that before the time t is equals to 4 seconds, it was open. So I have to get the voltage at that point, because when I close the switch, the voltage of the capacitor will not change. The capacitor resists abrupt changes. The analysis of circuits containing inductors or capacitors is dependent upon the formulation and solution of the integral differential equations that characterize the circuit. So these equations, we usually call it homogeneous linear differential equations. So if you are new to first order differential equations or second order differential or general differential equations, I will advise you to revise them, or you should go and learn first order and second order differential equations. We use first order differential equations to solve the response of a circuit. So the solution of the differential equation represents a response of the circuit, and it is known by many names. Since the response depends upon the general nature of the circuit, what do I mean by that? That is the type of elements, their sizes, the interconnection of the elements. It is often called a natural response. However, any circuit we construct cannot store energy forever, right? The resistances intrinsically associated with inductors and capacitors will eventually convert all stored energy into it. The response must eventually die out, and for this reason, it is frequently referred to as the transient response. So natural response and transient response denotes the same thing. Energy is stored on inductors and capacitors, and of course they must lose it. They must lose the energy either as heat or in another form of energy, and the way they lose their energy is transient, that is, it's exponential. What of when we consider independent sources acting on the circuit? So the part of the response will resemble the nature of a particular source or forcing function. This part of the response, called the particular solution, is called the steady state response or the forced response. If you go back to your first order circuits, right, so there's usually a complementary function and a particular integral. Like I said, if you don't understand these terms, you should have to visit this. This is not an engineering mathematics tutorial, but this is a circuit analysis tutorial. So let us begin our study of transient analysis by considering the simple series RL circuit. So what I will try to explain here is that in this video we'll talk about RL circuits, that is resistor and inductors circuits, a circuit that contains resistors and inductors only. So in the second video that after this video, I will talk about RC circuits. I'll talk about RC circuits, that is circuits containing resistors and capacitors only. So under these RL circuits, I'll talk about source-free RL circuits, that is circuits that does not have a source, a circuit that is not driven, right? A circuit that is not forced, that is doesn't have a voltage source or a current source. So in this case, we only talk about the transient response, the natural response. naturally, how the inductor will respond naturally without any forcing function, without forcing it. So when you add the source, it means that you are forcing the inductor to respond. So in the second part of this video, I will talk about driven response. And there I cannot talk about complete response, that is the natural response plus the forced response. So that is if you have a circuit, it contains resistor, inductor, and sources. So, and of course we have a switch. How do we get a complete response of the circuit? And of course we use first order differential equation to solve these equations. So if you apply KVL to the circuit, what do we have? We have what? VL, it enters the plus. You can say minus VR equals 0, right? But if you don't want to use the voltages that are already being added here, so what do? It will be what? What is the voltage on L? It's L di dt. Am I right? Then plus Ri. That is, it enters the resistor. The voltage there is Ri. So we are not considering the terminals that were put there. So it's equals to 0. Dividing both sides by L, what do we have? We have di dt plus R over Li equals 0. This is a first order differential equation, and of course we are going to use first order differential methods to solve it. And if you look at this very well, the easiest way to solve it is to apply separation of variables method. So you have to separate the variables and we integrate the results. So separating the variables, what do we have? We have to bring this to the other side. So there we have what? Di dt is equals to minus R over Li. So, and of course, if I separate the variables, that is bringing I to this side, bringing others to the right hand side, I will have 1 over I di is equals to minus R over L dt. And of course, if I integrate both sides, and assuming that the initial time is t is equals to 0, and the final time is t, right? So we have what? I of 0 and I of t. So if you do that, if you integrate 1 over I, we will have ln I from I naught to I, and this is 1 naught R over L from 0 to t. Imputing the boundaries, we have ln I minus ln I naught is equals to minus R over L t minus 0. So what does that give us? Ln I minus ln I naught. According to the laws of logarithm, it will become ln I over I naught is equals to what? Minus R over L t. And therefore, according to the laws of logarithm, I over I naught will be equals to what? E raised to power minus R over L t. How does this E come into place? Ln is same thing as log E. It's called natural logarithm. So if I say log E B, right, is equals to something, let me say A, it means that B is equals to E raised to power A. So that's the law of logarithm. So and therefore I can say that my I of t is equals to I of 0 E raised to power minus R over L t. So this is the natural response for an RL circuit. That's very, very straightforward. That's the natural response of an RL circuit. And let's take an example. If we take an example, that is, we have an inductor here in series with a resistor, and we have 50 milliohms and 200 ohms, 50 millihenry, sorry, and 200 ohms. So how do we get our natural response? That is, let us get the expression for IL of t, that is the current moving through the inductor. IL of t, that is valid for t greater than 0. So that's very, very straightforward. IL what? Because to I naught e raised to power minus Ri over L, RT over L. So which means that we need to have the initial current, and let's say that the initial current is 2 amperes, that is I naught is equals to 2 amperes. Therefore the current as t greater than 0 will be 2 e raised to power minus, what is R? 200 t over what is L? 50 microhenry, that's 10 raised to power minus 3. And if you divide that, you find IL of t to be 2 e raised to power minus 4000 t amperes, and that is the answer. You can see how simple it is. So from this equation, we usually write our general equation as IL is equals to I naught e raised to power minus t over tau, where tau is the time constant. And if you compare this to this equation here, so what does our tau mean? It means our tau is L over R, and the unit is in seconds. So that's our time constant. So now let's talk about driven RL circuits. What does that mean? I already said it that driven RL circuits means forced RL circuits. That is when we have a source in our circuit. So that is we have a resistor, an inductor, and the RL circuit is forced. That is, it has a source. It is not responding naturally again. It's not bringing out the forced response. Right. So plus, minus. This is R, this is L, and of course this is V naught. So this is very, very straightforward. Let us apply KVL and let's see the response we have. And of course this is IL, that is the current moving through the inductor, IL. So applying KVL, so what do we have? We have Ri, right, plus L di dt. Ri is the voltage on resistor, L di dt is the voltage on the inductor, minus V naught equals 0. So what does that mean? We have Ri plus L di dt equals to V naught. That's very, very straightforward. So in the same way, we'll apply separation of variables. And how do we do that? It's very, very simple. So we separate the I, we separate the t, because that's the only two variables we have here. So if I bring Ri to the other side, and we have L di dt equals to what? V naught minus Ri. So this term contains I, so I can bring it to the other side. So I will have what? L over V naught minus Ri di is equals to dt, and therefore I can integrate both sides. So I have I naught, I have I. If I integrate this, I have 0 and t. So if I integrate both sides, what will I have? That's very, very simple. If you don't know how to integrate, you have to go and revise that too. You must know how to integrate as an engineering student or as an impending engineer. So integrating that, what do we have? We have L over V naught minus Ri, so which means that we'll differentiate this to have V naught, right? And of course, when differentiate this, we have minus R, not V naught. We have minus R, and therefore we divide this by minus R. So that gives us minus L over R, because we have L on top before, and when we integrate something like that is in the denominator, usually it turns to a logarithmic equation, ln V naught minus Ri. And when we integrate with respect to t, the right hand side, what do we have? We have t, and of course from 0 to t, this is from I naught to I. Okay, so when we assume that the I of I naught is equals to 0, right, when t is equals to 0, so what we have is what? When we input that, we have minus L over R ln, let me put this in the bracket, ln V naught minus Ri. So that's for the upper limit, and for the lower limit, when we put I is equals to 0, we just have ln V naught, and therefore it will be equals to t. Do we understand that? And of course, by the laws of logarithm, this will turn minus L over R ln V naught minus Ri over V naught is equals to t. And by laws of logarithm 2, another law of logarithm, right, this will turn to raised to power. That is, anything in front of the logarithm function, we can bring it to the power of what is inside. So what does that mean? I have what? Ln V naught minus Ri over V naught raised to power minus L over R equals t. So what does that give me? According to another law of logarithm, it means that this will turn to e raised to power t. Am I right? So what does that give me? I have V naught minus Ri over V naught raised to power minus L over R. It will be equals to E raised to power T, right? If we take the power of both sides, if you raise the power of both sides to minus R over L, minus R over L. So this cancels this cancels this, minus cancel minus. So we have V naught minus Ri over V naught equals to E raised to power minus RT over L. And what does that mean? It means that if I make I the solid formula, I will have I to be equals to V naught over R minus V naught over R E raised to power minus RT over L, which is the same thing as V naught over R into brackets 1 minus E raised to power minus R over LT. And this actually contains two parts. You can see that this is almost the same as our natural response. Our natural response is I naught E raised to power minus RT over L. This is our natural response. And what is I naught? I naught is what? V naught over R. So this is the natural response, also called the transient response. And this is the first response, V naught over R. How do I get the first response without going through all this? So the first response is, I told you that an inductor acts as a short circuit to DC. So this is a DC source, right? It will act as a short circuit, and therefore we will have something like this. We have a resistor, then this is the short circuit, and of course the source. And of course we have IN. The current is still there. It's only the voltage of the inductor that is 0. So plus minus V naught. So because it is forcing it, it turns to a short circuit. So this is R, and of course I want to get IL. What would that be? IL will be equals to V naught over R. That's Ohm's law. Straightforward. So this is the first response, and you can see that that is what we have here. This is the transient response, and this is the first response. As simple as that. So let us take an example. So this is an example to showcase the first and the natural response. So we have a source. This u of t minus 3 is called a unit step function. So unit step function u of t means that it is equals to 1 when t is greater than 0 and 0 elsewhere. So if I draw that as a graph, it means that at 0 it is 1 till infinity, but anything less than 0 it is 0, right? So for u of t minus 3, what would that be? U of t minus 3 means that we shift it 3 times. This is 1, this is 2, and this is 3. So which means that at t is equals to 3, right, it is 1. Anything less than 3, it is 0. So what does that mean? It means that this source will start forcing the inductor when t is equals to 3. So when t is not up to 3, when the time is not up to 3 seconds, the source is not present in the circuit. It is just a natural response. That will be a natural response of the inductor that will be happening. So if you want to get the final response, so what do we have? We have to get the first response. The first response, right? And that is very, very straightforward. So first response is this inductor will turn to a short circuit, and when we redraw that, we have what? We have this, the resistor, and of course this is the source, right? Plus minus 12 volts. So there's no need for ut of minus 3. That one is just telling us that when t is equals to 3, that's when the source comes into play. And this is 1 kilo ohms. Right, so how do I get I? So the I first, it is also known as I of infinity. That is, I as time tends to infinity. I of infinity is what? V naught over R. Don't forget, V naught over R. So what is V? 12. So we have 12 over 1000. And that will give me 12 milliamperes. That's 12 milliamperes. So I already have that. I have V naught over R to be 12 milliamperes. And of course, what is R over L? The time constant. Time constant tau is what? L over R. So L is 50 times 10 raised to the power minus 3 and R is 1000. So that will give me 50 times 10 raised to the power minus 6 seconds. So this is the time constant. So if I want to write the equation right now, I will have I of t minus 3. Don't forget, the current starts having complete response when t is equals to 3. So it is equals to V naught over R is 12 minus 12 e raised to power minus t over tau. Tau is 50 times 10 raised to power minus 6. Right? T. Okay? And that's it. And of course, you have to put u of t minus 3. Why? Because it starts from when t is equals to 3. So what do we have here? We have 12 minus 12 e raised to power minus 20,000. 1 over 50 times 10 to the power minus 6 is 20,000 T. So this is the answer for our complete response. And that's straightforward. That's straightforward. So this is the circuit we'll be using to explain better what natural and forced response is. So the question says that we have 50 volts here and we have 50 U of T here. This 50 volts means that for all time, whether T is less than 0 or not, right, the source, the circuit will still have 50 volts. But when T is not equals to 0 yet, right, that is, it does not reach T is equals to 0, there is no source here. So the only source that exists is this. And when T is greater than 0, the two sources exist. Right, so first let's get our time constant. Time constant tau is what? L over R. So what is R? Our R is usually the equivalent resistance because we have two R here, right? And how do we get equivalent resistance? We'll turn off our sources and we'll calculate our equivalent resistance. So when we turn off our sources, what do we have? This will become a short circuit, this will become a short circuit. So I will have 2 ohms in parallel to 6 ohms. 6 and 2. So what is Req? Req is equal to what? 2 times 6 over 2 plus 6. So that gives what? 12 over 8, which is what? 1.5 ohms. So which means that the time constant is equals to 3 over 1.5, which is equals to 2 seconds. Right? That's very easy. So, and what is the current? The question is that we should get the value of the current going through the inductor for all values of time in the circuit. I of t for all values that is less than 0 or greater than 0. So let's get natural response because of course our complete response is what? The forced response plus the natural response. So the natural response here is basically very simple. The natural response, don't forget, is what? Let's call this I naught e raised to power minus t over tau. Right, so don't forget this. So I know that our tau is 2. So what does that mean? It's equals to I naught e raised to power minus t over 2 amperes. So how do we get I naught? We'll get I naught later. So this current here is for when t is greater than 0. Why? Because it must be decaying. If t is less than 0, this will become negative, and of course our exponential will now be a positive, and it's not a decaying current again. If you draw the graph, it should be a decaying current, right? So but e raised to power positive is not decaying, it is moving to infinity. So that's why it is decaying. But if it is negative, and of course as t increases, the current is decaying, so which means that the current is reducing. So let's get our forcing function. So what do we do for first function? The inductor becomes a short circuit. So and if the inductor becomes a short circuit, what do we have as our current? Our current is basically 50 over 2. Let's draw the circuit. So this becomes a short circuit, right? So this is 50, this is 50 volts. This is of course U of t, and of course this is I of t. And this is a resistor 6 ohms, and this is 2 ohms. This is minus plus, and this is plus minus. So what would be our I of t? Remember that this is short circuit, and the short circuit is parallel to a resistor. Remember in circuit analysis, whenever a short circuit is parallel to any electrical component, no current will flow through that electrical component. So as the current is coming from the source here, it moves straight to the short circuit and goes back. Nothing enters here. That is I is equals to 0 here. So what does that mean? We want to get, so which means that the circuit becomes what? 50 plus 50 is 100. It means that I have a resistor 2 ohms, a short circuit, since the 6 ohm is a dead resistor, that is nothing goes through it. I have something like this. This is 2 ohms and this is 100 volts plus minus. So what will be I of t? I of t will be equals to 100 divided by 2 using Ohm's law. I of t is equals to 100 divided by 2 ohms, which is equals to 50 amperes. So our first response is 50 amperes. First response is 50 amperes. That's straightforward, right? So if now to get the complete response, which is what the natural response plus the first response. The natural response is I naught e raised to power minus t over 2, and the first response is 50. So, but we don't know what I naught is. How do we get that? I naught is when t is equals to 0, and at t is equals to 0, what do we have as I naught? Or if you check our circuit, when t is equals to 0, that is, remember that the inductor doesn't change at instantaneous time, right? So which means that t is equals to 0, there's no change because a source is added at t is equals to 0. So which means that there's no change in the inductor current at that t is equals to 0, even when they added the 50. So what does that mean? We have to get what the current is before the source was added. So, and that's what we call I of 0 minus. That is before 0 is actually 0, when it is coming from the negative side. So what is I of t? Because when it turns to 0 plus, that is after 0, it is still the same thing, which is same thing as I of 0. So we have to get I of 0 minus, which means that we are going to remove this source and get I of t. So what does that mean? It means that this will not be 100 again, this will just be 50. So this will not be 100 again, this will now be 50 volts. And of course, I of 0 minus will now be what? 50 divided by 2, which is equals to 25 amperes. Which is equals to 25 amperes. You can see how simple that is. So I of 0 is 25 amperes. So let's now put this in this equation to get what I naught will be. So at t is equals to 0, I is equals to 25. So what is I naught? That's very simple. I is 25 is equals to what? I naught e raised to power 0 plus 50. Am I right? Yes, I'm right. So what is I naught? E raised to power 0 is 1. So it means that I naught is equals to what? 25 minus 50, which is equals to minus 25 amperes. That's very simple, right? So if you have that, I can now put it back to our general equation, which is what the natural plus first response, which is that my I is equals to what? 50, which is the first response, and minus 25, because I naught is minus 25, e raised to power minus t over 2, and everything amperes. This is the answer for the current. So you see here that the first response is 50 amperes, right, and the natural response is this. So if I want to write it as a single expression, right, I can write it as I is equals to 25 plus 25 minus 25 e raised to power minus t over 2. So what does that mean? I'll have 25 plus 25, right, into bracket 1 minus e raised to power minus t over 2, and that's it. And this will be u of t, right, because this, which means that when t is less than 0, I will only be 25. That is, when this source has not been added, when this source here has not been added, the current will only be 25. But when t is greater than 0, it will carry everything, right? And that's it. So this is the correct answer. So that is all about RL circuit, the source-free RL circuit, driven RL circuit, complete response of the RL circuit. So let's now talk about RC circuit. It is similar to, I will talk about that in the next video. Thank you very much. See you in the next video.